Welcome to Grade 10 CBSE Physics class. I am Sudhi here. Today we are going to discuss about chapter number 4, magnetic effect of electric current. Magnetic effect of electric current. So first of all, I will divide the chapter into two parts. The first part is magnetism and the next part is electricity. The first part is magnetism and the second part is electricity. So first of all, we want to know that is there any relationship between magnetism and electricity? Is there any relationship between magnetism and electricity? From the part magnetism, as we all know that whenever the term magnetism heard, there is also another term related to magnetism called magnet. Whenever we heard the term electricity, there will be another term related to electricity called current. So here, is there any relationship between magnet and current, or is there any relationship between magnetism and electricity? That we want to study. Before moving to the chapter, I want to introduce an experiment which is conducted by Hans Christian Ørsted. So the experiment conducted by Hans Christian Ørsted consists of a straight conductor. So this is the straight conductor AB. So this is the experiment conducted by Hans Christian Ørsted. So AB is a straight conductor. He placed a compass near the straight conductor, or otherwise you have to say that a conductor. So he placed a straight conductor, and near to the straight conductor he placed a compass. The compass is used to know the direction. So inside the compass there is a needle, as you all know. Inside the compass there is a needle. That needle is a bar magnet. So this is a needle inside the compass. This is the needle inside the compass, and that needle is the bar magnet. So this is the conductor AB. What he do? That means what is the experiment conducted by, or what is the main theory related to the experiment conducted by Hans Christian Ørsted? First of all, he allows electric current to pass through the conductor. So what he do? First, he allows electric current, that is I, to pass through the conductor. He allows the electric current to pass through the conductor AB. So what he observed when electric current is passing through the conductor? He observes that the needle inside the compass deflects. What is his observation? His observation is the needle inside the compass deflects. The needle inside the compass deflects. So whenever electric current is passing through the conductor, he observes that the needle inside the compass deflects in one direction. Either it is anti-clockwise or it is clockwise. So then he allows, or otherwise we all know that electric current is a scalar quantity, but electric current has both a magnitude and direction. But it is a scalar quantity because it doesn't obey the law of vector addition. That's why electric current is a scalar quantity, but electric current has both a magnitude and direction. So he reverses the direction of electric current. Second, he reverses the direction of I. He reverses the direction of I. So first he allows electric current to pass through from B to A, then he allows the electric current to pass through from A to B. That is, his observation is that when he reverses the electric current, or otherwise we can say that when he reverses the direction of electric current, he observes that the deflection also reverses. The deflection also reverses. So first he allows electric current to pass through the conductor. When the electric current is passed through the conductor, he observes that the needle inside the compass deflects. The second thing he done is that he reverses the direction of electric current. When he reverses the direction of electric current, the deflection of the needle also reverses. And the third time, he increases the intensity of I he increases the intensity of electric current. So he increases the intensity means strength. He increases the strength of electric current. Then what he observes? He observes that the deflection also increases. So Hans Christian Ørsted done an experiment with an electric conductor and a compass. He placed a compass near the conductor. What is the peculiarity of the compass? Compass is used to find the direction. So here there is a needle inside the compass. That needle is a perfect bar magnet. So what the thing what all the things are he done in the experiment? First of all, he allows electric current to pass through the conductor. What is the observation? Whenever electric current passes through the conductor, the needle inside the compass deflects in one direction. So what he done in the second time? He reverses the direction of electric current. When he reverses the direction of electric current, the deflection also be reversed. Which means that in the first time, if the deflection is clockwise, then the next time the deflection is anti-clockwise. Whenever the direction of current changes, the deflection of the needle also changes. Whenever the current be reversed, the deflection also be reversed. Then the third time, he increases the strength of the electric current, or otherwise we can say that he increases the intensity of electric current. Whenever the intensity of electric current increases, the deflection also increases. These are the observations made by Hans Christian Ørsted in the experiment. What are the conclusions from the observation? So, from the observation, he concluded that whenever a current is passing through the conductor, a magnetic field is produced around the conductor. Whenever a current is passing through the conductor, a magnetic field B is produced around the conductor. That's why the needle inside the compass deflects. Already it is stated that the needle inside the compass is a bar magnet. If a bar magnet deflects, that means that there is a magnetic effect is produced. So there is a magnetic effect is produced. That's why the bar magnet is, or otherwise the bar magnet deflects. So when the bar magnet deflects, whenever current is passing through the conductor. That means that whenever current is passing through the conductor, or whenever the current is passing through the conductor, a magnetic field is produced, or otherwise we can say that a magnetic effect is produced. Due to that effect or due to that field, the needle inside the compass deflects. So he concluded that, Hans Christian Ørsted concluded that whenever a current is passing through the conductor, a magnetic effect or a magnetic field is produced around the conductor. So that effect is called magnetic effect of electric current. He concluded the statement on the basis of the observation made by Hans Christian Ørsted. What are the observations made by Hans Christian Ørsted? First of all, he allows electric current to pass through the conductor. Whenever electric current passes through the conductor, the needle inside the compass deflects in one direction. And then he reverses the direction of electric current. He observes that the deflection also be reversed. And finally, he observed that whenever intensity of electric current increases or strength of electric current increases, the deflection also increases. From all these observations, he clears that, or he concluded that whenever current is passing through the conductor, a magnetic effect is produced. That's why the needle inside the compass deflects. So the magnetic field is produced and the needle inside the compass deflects, which means that the needle inside the compass is a bar magnet. So due to that magnetic field, the bar magnet deflects. Which magnetic field? The magnetic field produced due to the current. So this is the conclusion such that whenever a current is produced or a current is passing through a conductor, a magnetic effect, or otherwise we can say that a magnetic field is produced around the conductor, and that effect is called magnetic effect of electric current. This is experimentally proved by the scientist called Hans Christian Oster. That's all about magnetic effect of electric current. Our next topic is magnetic field. Magnetic field. What is meant by magnetic field? Magnetic field means that the space around a magnet where the influence of magnet or magnetic force can be felt. Here is a magnet. This is the north pole of the magnet and this is the south pole of the magnet. And here is another magnet. This is the north pole and this is the south pole. As we all know that opposite poles of the magnet attracts each other. Opposite poles of the magnet attracts each other. That means that the south pole and north pole attracts each other. But for the attraction, it is not a must that, or otherwise we can say that for the attraction, the thing is that the south pole and north pole attracts each other. That means that there is a field is produced around the magnet. There is a field is produced around the magnet, or otherwise we can say that there is a space is created by the magnet where the influence of that magnet is in that space. So here we can say that if it is a magnet is here, this is the magnet, north pole and south pole. This magnet creates a space of its own. This is the space created by the magnet. And in that space, each and every point, there is a presence of the magnet. There is a presence of the magnet, or otherwise we can say that there is a presence of the magnetic force created by the magnet. That means that this is the space created by the magnet where the influence of the magnet can be found. That space is called magnetic field. That space is called magnetic field. So what is meant by magnetic field? Magnetic field means the space around a magnet. The space around a magnet where the influence of magnet or magnetic force can be felt. So the space around a magnet where the influence of magnet or magnetic force can be felt is called a magnetic field. So inside the magnetic field, at each and every point, there is a presence of the magnet or the presence of the magnetic force created by that magnet. And the next term is intensity of magnetic field, or otherwise we can say that strength of magnetic field. Strength of magnetic field. Strength of magnetic field, which is denoted by the letter B. So here is a magnet and this is the space created by the magnet. Theoretically, as we all know that theoretically the magnetic field is up to infinity, but practically it is not possible. So here is the magnetic field created by the magnet and this is the point, each and every point I mark. Each and every point there is a presence of the magnetic field, or otherwise we can say that there is a presence of the magnet or the magnetic force produced by the magnet. So consider this point and consider this point. This point is close to the magnet. This point is close to the magnet and this point is somewhat far away. As we consider these 2 points, this point is close to the magnet and this point is far away from the magnet. So what about the strength of these 2 points? This point is marked as A and this point is marked as B, which means that the strength at A is greater than the strength at B. The strength of the magnetic field at A is greater than the strength of the magnetic field at B, which simply indicates that whenever the distance increases, the strength of the magnetic field decreases. Whenever the distance increases, the strength of the magnetic field decreases. So we can state as the strength of the magnetic field, the strength of the magnetic field, the strength of the magnetic field is inversely proportional to the distance. The strength of the magnetic field is inversely proportional to the distance, which means that whenever the distance increases, the strength of the magnetic field decreases. But there is a presence of magnet each and every point inside the field. For each and every point inside the field, there is the presence of magnet or the presence of magnetic field or the presence of the magnetic force produced by the magnet. But the thing is that whenever the distance increases, the strength of the magnetic field decreases. The strength of the magnetic field varies. The strength of the magnetic field varies with respect to the distance. If the point is very close to the magnet, then the strength will be on the higher side. If the point is far away from the magnet, then the strength of the magnetic field is very weak. That means that the strength of the magnetic field is inversely proportional to the distance. So we can write B is inversely proportional to, if R is the distance, we can say that B is inversely proportional to R, or B is inversely proportional to D, where D is the distance. If D is the distance, D is inversely proportional to D. If R is the distance, B is inversely proportional to R. The next thing is that magnetic field lines. Magnetic field lines. So here is the magnet. It's a bar magnet. The north pole of the bar magnet, the south pole of the bar magnet. This line is called a magnetic field lines. That means the first point related to magnetic field line is that the imaginary line originating from the north pole, and terminates to the south pole. Terminates means moving towards. Terminates to the south pole is called magnetic field line. The first statement regarding magnetic field line is that the imaginary line originating from the north pole and terminates to the south pole is called magnetic field lines, or otherwise we can say that magnetic field lines originating from the north pole and terminates to the south pole. The second thing is that the tangent at any point on the magnetic field lines gives the direction of direction of magnetic field at that point. The tangent at any point on the magnetic field lines gives the direction of magnetic field at that point, which means that here this is the magnetic field line. This is a magnetic field line. I will mark the point here, and this is the point A. How to find the direction at the point A, or otherwise I want to know the direction of magnetic field at the point A. First of all, draw a tangent at the point A. Draw a tangent at the point A. That tangent will give the direction of magnetic field at the point A. Here I mark another point B. I want to know the direction of magnetic field at the point B. I draw a tangent at B, and this tangent will give the direction of magnetic field at B. So if we want to find out the direction of magnetic field at a point, then we draw a tangent at that point. That tangent will give the direction of magnetic field at that point. So what is the use of tangent there? The tangent at the point will give the direction of magnetic field at that point. So here the tangent is like this, and here is like this. That means that this tangent will give the direction of magnetic field at A, and this tangent will give the direction of magnetic field at B. So the second characteristics related to the magnetic field line is that the tangent at any point on the magnetic field line gives the direction of magnetic field at that point. The third point is that, which is an important point, magnetic field lines never intersect each other. Magnetic field lines never intersect each other. No two magnetic field lines intersect each other. That means that here is a magnet, and this is the north pole, and this is the south pole. So here, this is the first magnetic field line, and this is the second magnetic field line. At this point P, if the magnet, this is wrong, this is actually, this is wrong. If they intersect each other, if they intersect each other, if they intersect each other at the point P, it will mean that at the point of intersection there will be two tangents. At the point of intersection there will be two tangents, which means that there is two direction at the same point. Actually we know that the tangent at any point on the magnetic field line gives the direction of magnetic field at that point. If the magnetic field line intersect each other, at the point of intersection there will be two tangents. That two tangents indicates two directions. In a same point, it is not possible to get the two directions. In the same point, there will be only one direction. So if we draw two tangents at the same point, then it indicates that there will be two directions at the same point, which is never possible, which is impossible. That means that magnetic field line never intersect each other. If they intersect each other, if they intersect each other, if they intersect each other, it would mean that at the point of intersection, at the point of intersection, at the point of intersection, it has two directions. It means magnetic field has two directions. At the point of intersection, magnetic field has two directions. That means it has two directions, which is not possible. Which is not possible. So this is the thing. So there will be 3 points regarding magnetic field lines. Magnetic field lines are imaginary lines like the equator of the earth. Like the equator of the earth, the magnetic field lines are imaginary lines. Corresponding to magnetic field lines, there is imaginary lines associated with the charge. That lines are called, that imaginary lines associated with the charge are called electric field lines, and the electric field lines originating from the positive charge and terminates to the negative charge. Here in the case of magnet, the imaginary line associated with the magnet is called magnetic field lines. Magnetic field lines originating from the north pole and terminates to the south pole. The tangent at any point on the magnetic field lines gives the direction of magnetic field at that point, and the magnetic field line never intersect each other. If they intersect each other, it would mean that at the point of intersection, magnetic field has two different directions. Magnetic field has two different directions, which is not possible. For a single point, two direction is not possible. That's why we can say that magnetic field line never intersect each other. That's all about magnetic field and magnetic field line. So right now we want to discuss about magnetic field due to a circular loop, and the next one is magnetic field due to a solenoid. Magnetic field due to a solenoid. What is mean by what is in the case of magnetic field due to a circular loop? Here is a circular loop and this is the magnetic field. So when it comes away from the wire, the circles are bigger. When it comes away from the wire, the circles are bigger. And right now, at the center, it will be a straight line. At the center, it will be a straight line. What are the factors affecting magnetic field due to or the strength of the magnetic field? Factors affecting strength of the magnetic field in the case of a circular loop. Strength of the magnetic field in the case of a circular loop. So there will be two factors affecting the strength of the magnetic field in the case of a circular loop. The first one is current and the second one is radius of the loop. The first one is current and the second one is radius of the loop. So the strength of the magnetic field in the case of a circular loop, there will be two factors are dependent. The two factors are current and the radius of the circular loop. How current depends on the circular loop? So more current, more strength. That means the current is directly proportional to the strength, or otherwise we can say that the strength of the magnetic field here is directly proportional to the current. Whenever the current increases, the strength also increases. What about the radius of the loop and the strength? The strength of the magnetic field is inversely proportional to the radius of the loop. Whenever the radius of the loop increases, the strength of the magnetic field decreases. Whenever the radius of the magnetic field increases, the strength of the magnetic field decreases. Also, here there will be only one loop. There is a magnetic field. If the loop is doubled, that means there will be two loops. Then the magnetic field is doubled. We got the double magnetic field than in the initial case when the loop is increasing, when the loop is doubled. That means that when the loop is of n loop, that means if there will be n loops are there, the magnetic field is n times than the initial one. So that's the case in the case of a circular loop. That is the magnetic field due to a circular loop. This is a pictorial representation of the magnetic field due to a circular loop. It is clear that in the center, the magnetic field is a straight line. So this is in the case of a magnetic field due to a circular loop, and in the case of a magnetic field due to a circular loop, the strength of the magnetic field depends upon two factors, current and the radius of the loop. Whenever the current increases, the radius also increases. Whenever the current increases, the strength of the magnetic field increases. Whenever the radius of the loop increases, the strength of the magnetic field decreases. That is, the strength of the magnetic field is directly proportional to the current and inversely proportional to the radius of the loop. Next one is solenoid. What is a solenoid? Solenoid is, simply we can say that, cylindrical winding of conducting wires in a coil. the cylindrical winding of conducting wires in a coil, or the winding of conducting wires in a coil, like this. This is coils. This coil is binded in a this conducting coils is binded in a cylindrical shaped thing, then it is called a solenoid. So it's a number of turns. There will be number of turns in the case of a solenoid. So magnetic field, we want to discuss about the magnetic field due to a solenoid. In the case of the magnetic field due to a solenoid, whenever current is passing through the solenoid, that solenoid will act as a bar magnet. Whenever current is passing through a solenoid, that solenoid will act as a bar magnet. Therefore, the magnetic field due to a solenoid we can draw in such a way that this is the north pole and this is the south pole. In such a way that outside the bar magnet, the direction of magnetic field line is from north pole to south pole, and inside the bar magnet it is from south pole to north pole. So this is the direction. So whenever current is passing through a solenoid, that solenoid will act as a bar magnet, and the magnetic field lines through a bar magnet is like this. Outside the bar magnet, the direction of the magnetic field line is from north pole to south pole. As we all know that the magnetic field lines originating from the north pole and terminates to the south pole. But inside the bar magnet, the direction is reversed such that it is from south pole to north pole. So whenever the current is passing through a solenoid, one end of the solenoid acts as magnetic north pole and the other end is act as the magnetic south pole. That's why we can say that whenever current is passing through a solenoid, what happens? That solenoid will act as a bar magnet. So the strength of the magnetic field due to a solenoid is on the higher side. Why? Because there will be number of coils. There will be lot of coils in the case of a solenoid. But in the case of a circular loop, as we compare the circular loop with the solenoid, here we draw only one loop. But in the case of a solenoid, there will be lot of turns are there. So number of turns, number of coils are winded in a cylindrical shape, or otherwise we can say that the coils are winded in a particular manner, then that is said to be a solenoid. And in the case of a solenoid, there will be lot of turns are there, so number of coils is higher. So whenever the number of coils is higher, the current passing through the coils are also, or the current passing through the specimen is also on the higher side. So then whenever the number of coils increases, the current passage through them is also increases. That means that the magnetic field strength also increases. As we know that the current is directly proportional to the magnetic field. So whenever the strength of the magnetic field is directly proportional to the current passing through the coil, that means that there will be a lot of coils are there. Whenever the number of coils increases, the current passing through them also increases. Whenever the current passing through them also increases, the strength of the magnetic field also increases. So solenoid produces a magnetic field of higher strength. That's why solenoid can be used as an electromagnet. This can be used as an electromagnet. What is meant by electromagnet? The specimen which shows magnetism under the influence of electricity. The specimen which shows magnetism under the influence of electricity is called electromagnet. Whenever the current through the specimen is switched off, the magnetism eliminates, or otherwise we can say that there will be no magnetism in the absence of electricity. So whenever current is passing through a specimen, and if that specimen shows magnetic effect or magnetism, then that specimen is said to be an electromagnet. So under the influence of electricity, if a specimen shows magnetism, then that is said to be an electromagnet. Solenoid can be used as an electromagnet. Why? Because the strength of the magnetic field in the case of a solenoid is on the higher side. Why the strength of the magnetic field in the case of a solenoid is very high? Because solenoid consists of number of turns. Whenever the number of turns increases, the current also increases. Whenever the current increases, the magnetic field strength also increases. In the case of a solenoid, there will be a lot of turns are there. Therefore, the current through the solenoid is on the higher side. Therefore, the magnetic field strength is on the higher side. That is the reason why solenoid can be used as an electromagnet. So what is meant by an electromagnet? A specimen which acts as a magnet under the influence of an electricity. A specimen or a material which act as a magnet under the influence of electricity is called electromagnet. That means that whenever the electricity is cut down or whenever the electricity is shut down, that means that whenever the electricity is shut down or whenever the current through the material is switched off, it there will be no chance it will act as a magnet. So under the influence of electricity only it will act as a magnet. So that is called electromagnet. So in the presence of electricity it will act as a magnet. That specimen will act as a magnet. So that is called electromagnet. A solenoid can be act as an electromagnet or solenoid can be used as an electromagnet because the strength of the magnetic field in the case of a solenoid is on the higher side. That's all about magnetic field due to a circular loop and magnetic field due to a solenoid. Now moving to the next topic, force acting on a current carrying conductor. Force acting on a current carrying conductor. On a current carrying conductor. So the force acting on a current carrying conductor is simply called magnetic Lorentz force. The force acting on a current carrying conductor is simply called here is magnetic Lorentz force. What is meant by magnetic Lorentz force? The force experienced on a charge. The force experienced on a charge moving in an external magnetic field. The force experienced on a charged particle or a charged particle moving in an external magnetic field. The force experienced on a charged particle moving in an external magnetic field is called a magnetic Lorentz force. Here, as we all know that moving charges constitute current. So here we know that force acting on a current carrying conductor. Here whenever the charged particle moving, that means there is a current is developed. So here the current carrying conductor is moving in an external magnetic field. So if the current carrying conductor is not moving, it is placed in an external magnetic field conductor. It is placed in an external magnetic field. The charge is moving in the current carrying conductor. So the force experienced on a current carrying conductor when the current carrying conductor is placed in an external magnetic field is called a magnetic Lorentz force. When the current carrying conductor is placed in an external magnetic field, the force experienced on the current carrying conductor is called a magnetic Lorentz force. Magnetic Lorentz force, which is denoted by F. Magnetic Lorentz force F. So what is meant by magnetic Lorentz force? The force experienced on a charged particle moving in an external magnetic field. That's why when a current carrying conductor is placed in an external magnetic field, the force experienced on the current carrying conductor is called a magnetic Lorentz force, or otherwise simply said to be Lorentz force. So there will be Lorentz force are of two types, magnetic Lorentz force and electric Lorentz force. So you have to specify it is magnetic Lorentz force. So whenever the current carrying conductor is placed in an external magnetic field, the force experienced on the current carrying conductor is called a magnetic Lorentz force. The force depends upon three factors. Number one, strength of the magnetic field. Strength of the magnetic field. B. The second one, length of the conductor. Length of the conductor. L. The third factor where the force depends is current passing through the conductor. Current passing through the conductor. Current passing through the conductor. I. How they are depends on the force. Whenever the strength of the magnetic field increases, the force also increases. Whenever the strength of the magnetic field increases, the force also increases. Whenever the length of the conductor increases, the force also increases. Whenever the current passing through the conductor increases, the force also increases. All they are depends on directly proportional. So the strength, length, and the current passing through the conductor depends upon the force. Or otherwise, we have to say that the force acting on the current carrying conductor depends upon the strength of the magnetic field, current passing through the conductor, and finally the length of the conductor. So that's all about the force acting on a current carrying conductor. So simply the force acting on a current carrying conductor which is placed in an external magnetic field is called a magnetic Lorentz force. More simply, the force acting on a charged particle moving in an external magnetic field is called a magnetic Lorentz force. Magnetic Lorentz force depends upon three factors called length of the conductor, current passing through the conductor, and the strength of the magnetic field. How to find the direction of the force in the external magnetic field? The direction of the force can be found out by using Fleming's left hand rule. Fleming's left hand. The direction of the force can be found out. That means the direction of the magnetic Lorentz force can be found out by using Fleming's left hand rule. Fleming's left hand rule. How we can determine Fleming's left hand rule? Fleming's left hand rule. So Fleming's left hand rule. According to Fleming's left hand rule, stretch the forefinger, middle finger, and thumb finger of the left hand in mutually perpendicular direction. Forefinger, middle finger, and thumb finger of the left hand in mutually perpendicular direction. If the middle finger gives the direction of current and the forefinger gives the direction of magnetic field, then the thumb finger gives the direction of magnetic Lorentz force or simply force. The middle finger gives the direction of current, the forefinger gives the direction of magnetic field, then the thumb finger gives the direction of magnetic Lorentz force or otherwise simply force. So I will draw. This is the thumb finger. This is the forefinger, or otherwise we have to say that the index finger, and this is the middle finger. So the middle finger gives the direction of current. The index finger gives or the forefinger gives the direction of magnetic field. Then the thumb finger gives the direction of magnetic Lorentz force. So this is Fleming's left hand rule. According to Fleming's left hand rule, stretch the forefinger, middle finger, and thumb finger in mutually perpendicular direction. That means the angle between them is 90 degree. So what about the angle between the thumb force and field? Force and field, the angle is 90 degree. Then this is 90 degree. This is also 90 degree. All of them are mutually perpendicular. That means that the force and field current all are in mutually perpendicular direction. So as we know that when the current is passing through a conductor, a magnetic field is produced around the conductor and there is a force is generated and that force is called a magnetic Lorentz force. All are mutually perpendicular. According to Fleming's left hand rule, we can find out the direction of force, field and current. So the middle finger gives the current, the forefinger gives the magnetic field and the thumb finger gives the magnetic Lorentz force or otherwise simply said to be force. That's all about magnetic Lorentz force and Fleming's left hand. Now moving to the next topic, alternating current and direct current. Alternating current, AC and DC. Alternating current or direct current. The current that switches the direction periodically with the time is called alternating current. The current that switches the direction periodically with the time. Periodically with time. The current that switches the direction periodically with the time is called alternating current AC. So here is the diagrammatical representation of AC. So here AC consists of a positive half cycle and a negative half cycle. This positive and a negative half cycle constitute one cycle. One positive half cycle and one negative half cycle. This is the positive half cycle of AC. This is the positive half cycle of AC. And this is the negative half cycle of AC. Negative half cycle. So this positive half cycle and one negative half cycle, one positive half cycle and one negative half cycle constitute one cycle. So the current here, as in the figure, it clearly indicates that the current switches its direction periodically with the time. When with respect to the time, the current switches the direction. So the current that switches the direction periodically with respect to the time, then that current is called alternating current. So now we want to move that. What is mean by DC? Direct current. That means unidirectional current is called a direct current. Unidirectional current is called a direct current. So that's the difference between the current has only one direction. That is the unidirectional current is called a direct current. So the current that switches the direction periodically with respect to time is called alternating current. Here is the pictorial representation of alternating current. Alternating current consists of positive half cycles and a negative half cycle. One positive half cycle and one negative half cycle constitute one cycle. And in the case of direct current, the unidirectional flow of current is called a direct current. Now we want to analyze the main difference between AC and DC. Main difference between AC and DC. AC, DC. First point, current switches the direction periodically with the time. Next one, unidirectional current. DC is unidirectional current. Obtained from AC generator or from mains. Obtained from battery or from cell. Long distance, for long distance transmission, AC is used. Short distance transmission, DC is used. AC is more efficient than DC. DC is less efficient as compared to AC. So these are the main difference between AC and DC. Then we have to do a pictorial representation also in the difference. In the pictorial representation, this is AC and DC. This is the balance. AC, DC. 1, 2, 3. Fifth point is the pictorial representation. We can represent it picture wise. Here is AC and here is DC. Less power loss in the case of AC, but more power loss in the case of DC. If we consider long distance transmission. That's why for the long distance transmission, AC is preferred over DC because AC has less power loss and DC has more power loss as we compared with the AC. So these are the difference between AC and DC. What is mean by AC? The current that switches the direction periodically with respect to time, then that current is called alternating current, and unidirectional current is called a direct current. AC can be obtained from AC generator or from mains, and DC can be obtained from battery or from cell. For long distance transmission, AC is preferred. For short distance transmission, only DC is used. But more efficient. Which one is more efficient? AC is more efficient than DC. Then less power loss. So for if we consider long distance transmission, AC power loss is very less as we compared with the DC power loss. That's all about the difference between AC and DC. Now moving to the concept of time period and frequency of AC. 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 Time period frequency of AC. Here the pictorial representation of AC consists of a positive half cycle and a negative half cycle. So this is the positive half cycle and this is the negative half cycle of AC. This is the positive half cycle and this is again the negative half cycle. One positive half cycle and one negative half cycle constitute one cycle. What is time period of AC? Time period of AC. The time taken to complete one cycle is called time period of AC. The time taken to complete one cycle is called time period of AC. So here is one cycle. This is the time period. That means that this is the time period. That means that the time taken to complete one cycle. One cycle means one positive half cycle and one negative half cycle constitute one cycle. So this positive half cycle and this negative half cycle constitute one cycle. The time taken to complete one cycle is called time period of AC. Then we want to know about what is meant by frequency of AC. Frequency. Number of cycles in 1 second. Number of cycles in 1 second is called frequency. The unit of time period is second and the unit of frequency is hertz. So the time taken to complete one cycle is called the time period of AC. Frequency, that is number of cycles in 1 second is called a frequency. Number of cycles in 1 second is called frequency. There is a relationship between frequency and time period. Relation between frequency is denoted by small letter f. Frequency and time period. Frequency is the reciprocal of time period. Frequency is the reciprocal of time period. That we can write frequency f equal 1 by t. So the unit of frequency is hertz, unit of time period is seconds, and the frequency is the reciprocal of time period, and frequency is equal to 1 by t. If we consider the value of frequency of AC, it will be different in different countries, but the average value can be considered as 50 to 60 range. The average value of AC is considered as average value of AC in different countries can be considered as 50 hertz to 60 hertz. 50 hertz to 60 hertz. So that's all about the time period and frequency of AC. The time taken to complete one cycle is called the time period of AC. Number of cycles in 1 second is called the frequency. So the time period and frequency are mutually related. The time period is the reciprocal of frequency, or otherwise we can say that the frequency is the reciprocal of time period. The unit of time period is seconds and the unit of frequency is hertz. Finally, we want to know about the advantages of AC over DC. Advantages of AC over DC. What are the advantages of AC over DC? Advantages of AC over DC. So the first advantage is that it is more efficient than DC. AC is more efficient than DC because for long distance transmission, AC is preferred over DC. Because the reason is that power loss is very less. Power loss is very less. So for long distance transmission, because of these two reasons, because AC is more efficient than DC and the power loss of AC is very less, so for long distance transmission, AC is preferred over DC. And AC is easy to generate. Easy to generate. AC is easy to generate. And the generation is less cost. Generation costs the generation cost only very less as we compared with the DC cost. So the advantages of AC over DC is that it is more efficient than DC. The power loss is very less as we compared with the long distance transmission. Easy to generate and the less cost. The cost effective is AC as we compared alternating current with direct current. These are the advantages of AC over DC. That's all about the topic AC and DC. So moving to the final topic of the chapter called domestic electric circuit. In this circuit diagram, there will be three main wires are there. Neutral wire, live wire and earth wire. Earth wire is green in color, live wire is red in color and neutral wire is black in color. Then moving to a fuse. What is the use of fuse? Fuse protect the whole circuit from overheating and the overflow of current. Why fuse is used in circuit diagram we will discuss later. Then the electricity meter. Then moving to the distribution box. Then consist of lot of appliances are connected here. Lot of appliances are connected with the help of a 3-pin plug. And there will be a distribution box consist of lot of materials are there. So this is the circuit diagram, and here the earth wire is connected to one end of the appliances through a 3-pin plug. So what is the use of earth wire first? First we want to discuss about what is the use of earth wire. So earth wire is green in color. What is the use of earth wire in a circuit? So here earth wire doesn't carry any electricity. That is the first point. The earth wire doesn't carry electricity. one end of the earth wire is in earth. One end of the earth wire is in earth. And the other end is connected to the metal appliances, or the other end of the earth wire is connected to the metal appliances through a 3-pin plug. Through a 3-pin plug. Other end of the other end of the earth wire is connected to a metal appliances through a 3-pin plug. So what the use of earth wire there? If there will be by chance or otherwise accidentally, if the live wire touches the metal appliances, there is excess current flow through that metal appliances. That excess current will directly goes to earth with the help of this earth wire. So it is helping the person who is using the metal appliances from electric shock. So there is a chance of electric shock. If there will be any chance of electric shock, that the excess current passing through the metal appliances is passing through the earth wire and it will be grounded to the earth. The one end of the earth wire is grounded to the earth, so that excess current flowing to the earth through the earth wire. So then there is a chance of overloading. Overloading. What is mean by overloading? Overloading means excess appliances can be connected in a single socket. If this is a socket, there will be excess appliances are connected. What will happen if excess appliances are connected? If excess appliances are connected in a single socket, that single socket will draw lot of currents. That single socket will draw large amount of current. Due to that, the wire will be heating. There is a chance of overheating of the wire. Due to that overheating, there is a chance of fire. So that is called overloading. Due to overloading, there is a chance of short circuit also. Due to overloading, there is a chance of short circuit also. What is mean by overloading? If excess appliances are connected in a single socket, the socket will withdraw current, large amount of current, or otherwise we can say that that socket will draw large amount of current. Due to the large amount of current in a single socket, there is a chance of short circuiting, or otherwise we can say that there is a chance of fire. How fire is there? Because how it will be if there will be short circuiting are there, because if large amount of current is drawn by the socket, there is overheating in the wire and the wire will breaks and there is a chance of short circuiting at that time. What is mean by short circuiting? Actually, short circuiting is the direct contact of live wire and neutral wire. If the accidentally the live wire directly contacted with the neutral wire, then there is a chance of short circuiting and fire. So to protect all these, we have to fix a fuse in the circuit. We have to fix a fuse in the circuit. What is the use of fuse? The fuse wire in the fuse having low melting point. The fuse wire in the fuse have low melting point. If excess current passing through the fuse wire heats, and due to the low melting point of the fuse wire, it melts and the circuit breaks from here. If the circuit breaks from here, there will be no current flowing through the electric meter and the appliances. That is why the circuit is protected. So the fuse will act as a protective layer, or otherwise we can say that the fuse is act as a protective shield in the circuit. Why? Because the fuse wire, which is the fuse is made up of fuse wire, and that fuse wire has low melting point. When excess current is passing through the fuse wire, what happens? Due to the low melting point of fuse wire, whenever the excess current is passing through the fuse wire heats, and due to the low melting point, it breaks. Whenever the fuse wire breaks, then there will be no current flowing through electric meter and the distribution box and to the appliances. There will be no current flows through that. Therefore, the circuit is safe. So nowadays, in place of fuse, we will use MCB in place of fuse. So there is some difference between MCB and fuse. It's a new technology, MCB, and fuse is the old technology. What is the main difference between fuse and MCB is that Fuse works on the basis of heating effect of electric current. Fuse works on the basis of heating effect of electric current, and MCB works on the basis of magnetic effect of electric current. That's the main difference between fuse wire and MCB, or fuse and MCB. Fuse works on the basis of heating effect of electric current, and MCB works on the basis of magnetic effect of electric current. That's all about the domestic circuit. It consists of 3 wires: live wire, neutral wire, and earth wire. Earth wire is green in color, live wire is red in color, and neutral wire is black in color. Whenever the live wire and the neutral wire meets, whenever the live wire directly contacted with the neutral wire, there is a chance of short circuiting. Short circuiting is also, there will be a chance if there will be overloading is there. What is mean by overloading? If lot of appliances, that means excess appliances are connected in a single socket, then that socket will draw large amount of current. Due to the large amount of current, all the wires gets overheated and finally it will break. So due to that, there is a chance of short circuiting, and short circuiting simply means that when the live wire directly contracted with the neutral wire. So from the short circuiting and the excess amount of current passing through the appliances, the circuit is protected with a fuse. The fuse wire consists of a fuse wire with a low melting point. Whenever excess current passing through the fuse, due to the low melting point of the fuse wire, it will breaks immediately and stops the current to pass through the electricity meter, distribution box, and all the appliances. That's why the circuit is safe. Nowadays, in place of fuse, we use MCB. The main difference between fuse wire and MCB is that fuse works on the basis of, not fuse wire, fuse and MCB is that fuse works on the basis of heating effect of electric current, and MCB works on the basis of magnetic effect of electric current. That's all about domestic electric circuit. So the main topics including in the chapters are, first one is the experiment conducted by Hans Christian Ørsted. From that experiment, we concluded what is meant by magnetic effect of electric current. Then moving to the magnetic field, then magnetic field lines, why magnetic field lines never intersect each other. We know the reasons, such that if two magnetic field lines intersect each other, it would mean that at the point of intersection, the magnetic field has two different directions, which is not possible. Then moving to the bar magnet concept, then already we study about what is mean by magnetic field due to a solenoid, then magnetic field due to a circular loop, then magnetic Lorentz force, that is the force acting on a current carrying conductor in an external magnetic field. Then the direction of that force can be found out by using the magnetic Lorentz force, then alternating current, direct current, frequency of AC, then time period of AC, relation between frequency and the time period of AC, then advantages of AC over DC, then diagrammatical representation of AC and DC, then finally domestic electric circuit, short circuiting, fuse, what is meant by overloading, what is the colors indicating fuse wire, live wire, neutral wire, and earth wire, what is the use of earth wire in the circuit, like that. All are main points regarding this chapter. So that's all about the chapter magnetic effect of electric current. So I am Sudhi here, signing off from this class. Thanks for joining me in the class, and we will meet you soon in the next class. Thank you. Have a good day. Thank you all. We will see you in the next class.